Hello, let's continue with another example. The volume of a cube is increasing at 12 centimeters cubed per second. What is the rate of change of the side length when the volume is 27 centimeters cubed? So there's lots of translation we need to do here to figure out what we've got. So first thing is the volume of a cube is increasing at a rate at 12 centimeters cubed per second. So the volume is increasing at 12 centimeters cubed per second. So volume is increasing. So we're looking at centimeters cubed per second. So we're talking about dV dt is 12 centimeters cubed per second. That's the first thing I can say. If this had said it was decreasing, I would put a minus here, but it says it's increasing. I'm getting bigger, so I'm going to have a plus here. This is a positive number. If it had said decreasing, it would be negative. What is the rate of change of the side length? So that means I have what's the rate of change of the side length. So I need to pick a variable name. I'm talking about a cube, so let's draw a picture. As usual in maths, if we're able to, in a question, we should draw a picture. So we're dealing with a cube, and I'm going to call its side length x. It's a cube, so all the lengths are the same. And I have information about the volume. So I want the rate of change of the side length, which I've called x. So I want to know what the x dt is, how the side length is changing in time when the volume is 27 centimeters cubed. So I've been given the derivative of two variables in a single question. So I'm thinking I'm going to need to use my chain rule. I'm going to need to use my related rates of change to get how multiple things are changing at once. So I want to know what the x dt is. I'm going to say dx dt. So that's going to be equal to dx d something times d something dt. That's how my chain rule is going to work. Well, what does it make sense for me to have as my variable here? Well, in this case, it's going to be the volume. Could have been surface area if I was told about surface area of the cube, but in this case I was told about volume. So I have dV dt, so I'm going to need dx dv and dV dt. And again, this situation has occurred where I've ended up with dx dv is kind of a confusing thing to try and find for a cube. How's the side length changing as the volume of a cube changes? I usually think of volume of a cube the other way around. The volume of a cube would be x cubed. That's where we get the name cubed from, because it's the volume of a cube. So the point is we would be easily able to find dv dx. dv dx would just be 3x squared. But I've got dx dv. So if I end up with this situation like I did the last time, where I end up with something upside down, and I go, well, that would be easier to differentiate if I had the reciprocal of it. Just find the derivative of the reciprocal and then put it upside down. Which I'm going to do just here. So dx dv just means flip everything upside down. This won't always happen. It depends on what you pick as your derivative. I'll give you an example of that in just a moment. 1 all over 3x squared. Just to give you an example of what I'm talking about, if you happen to pick that you wanted to get dV dt by itself, you're given information about dV dt, so this is an aside, just to point out that this won't always happen. Sorry, I will put it down at the bottom here instead, so it's not disrupting the question too much. If I had picked dV dt as the thing I was going to break up, I'd end up with dv dx times dx dt. And I wouldn't have had to invert anything. I can find my dx dt is what I'm looking for, and dv dx is something I can easily find. It's just my 3x squared, and my dv dt is 12. So you could have ended up substituting in that way, depending on what you pick as your starting thing that you're going to break up with the chain rule. Depends on whether you're going to end up with something upside down or not. It will not always happen. It depends on what information you're given and how you end up picking to break it up. But if you see something that is upside down like this, you can just get the normal derivative and then flip your answer upside down. That's the key thing. It's just something that can be a stumbling block when you come across these questions and you end up with something that looks weird like this. It's just what we're already familiar with upside down. Now, I want my dx dt. I've now actually found my dx dv already. So I am going to just sub in. Is going to be 1 all over 3x squared. dv dt, I'm just given in the question is 12. So dx dt, I have 12 divided by 3 is 4, so I end up with 4 all over x squared. Now, I want to know what dx dt is when v is 27 centimeters cubed. But I have a little bit of an issue in that my formula that I have gotten here involves x. But I still know a relationship between v and x. So if I want to know what dx dt is, what dx dt is when v is 27 centimeters cubed, and I know stuff in terms of x, all I have to do is convert this into an equivalent x value. X cubed would be equal to 27. Get the cube root of both sides. Cube root does not cause us any problem. Well, we're dealing with lengths anyway, so we wouldn't have to deal with positive or negative, but a cube root preserves the sign, so you don't actually need to worry about plus or minus with a cube root. If you think about 3 numbers multiplied together, 3 negatives would give you a negative, as opposed to the problem we run into with our quadratics when we get the square root of stuff, that we could end up with plus or minus. That isn't an issue here. So what we're looking for, if we want to know what dx dt is equal to when v is 27, we're really looking for dx dt when x is 3. dx dt when x is equal to 3. All I'm going to have to do is sub in my value for x. I end up with 4 over 9. And the units for that, dx dt, would be length per time. And my length is in centimeters. And my time is in seconds. That's given to me because my volume was in centimeters cubed per second. So I know I'm dealing with centimeters and seconds. And that is what we need. Our general point is, if you're given multiple types of multiple variables, derivatives of multiple variables, and particularly if you're given shapes, so stuff like circles, spheres, cubes, or triangles. Shapes are big on this because we need formulas like this where we have the volume or the surface area or the area changing with respect to one variable, and how is it also going to change in time. That's the type of thing we will often use for related rates of change. And that is what we need for now.